Today we're going to do a quick review of fats. The longer version, of course, is on Brightspace, but this will just be a kind of quick rundown on everything. So let's start with when you make fats and why you make fats. So we started out talking about glycolysis. We took glucose, we went to pyruvate, took pyruvate to acetyl-CoA, did the Krebs cycle, did the stuff that makes ATP, did electron transport, and we made ATP for our cells. Then we said, well, there's a big underlying assumption in this. The underlying assumption is that we're making what we need when we need it in terms of ATP, and of course we don't. So then we talked about glycogen. Glycogen is our short-term storage. Then we said, well, we still have an assumption in there with the glycogen. With glycogen, we're assuming that we're eating or consuming the same amount of fuel or energy that we need. So it would be like saying we're using 2,000 calories a day to have a round number, and we're eating 2,000 calories a day. However, we know that's not necessarily the case, so we have a long-term storage molecule, and that's our fats or our fatty acids that, of course, we transport as triglycerides. So let's talk about how this works. Let's say first I don't know, burning 2,000 calories a day, but eating 6,000 calories. So what am I going to do? I've got a definite order of operations with this. So the first calories I eat will go glucose to pyruvate, do my Krebs cycle, electron transport, and make me ATP. But I'm still eating. So the next part of my calories then will go to glycogen. So again, glycogen is my short-term storage. Then, and only then, after I've filled up my glycogen, I'll fire up glycolysis again in the liver. I'll fire up the pyruvate dehydrogenase complex in the liver. But the Krebs cycle will say, nope, not me. You got enough energy. I'm not firing up. That will cause you to go and make fats. That will cause you to do lipo. Remember, anything starting with lip, acyl, or ester, you're going to think fats. So that'll make me do lipogenesis. Remember, genesis is generating. So here's my order of operations. It's kind of like when you get paid. Let's say, when we've said it a few times, you're paying yourself in your office the first of every month. What are you going to do first? First thing you're going to do is you're going to pay your bills that are due right now. So that's your ATP. Then, second part of your money, you will have calculated how much money do I need to get through until the first of next month. You know, gas, groceries, whatever. That's your glycogen. So that's your get you through until you get paid again amount of money or energy. Then the next part of your money will go to your fats. That's your long-term storage. That's the money that you're not planning on using for anything. You're saving that for whatever. So that's your fats. It's the third place that we go. So ATP first, short-term storage second, then we go to fats. Then let's turn the story around. Let's say now, instead of eating 2,000 calories a day, burning 2,000 a day and eating 6, let's say I'm doing it the other way around. Let's say I'm burning 6,000 even though I'm only eating 2,000. So now I'm burning 6,000. I'm running at a sustained caloric deficit. Now what do? Well, those 2,000 calories that I ate will go through all my stuff. Go glucose, pyruvate, acetyl-CoA, Krebs, electron transport, and make me ATP. But that's 2,000 calories and I need 6,000. So now what am I going to do? Then Next place I'll go looking for energy is my glycogen. I'll make glucose out of it and go through all my steps and make ATP. So I'll go to my second place. Then and only then, I still need calories, still need fuel, and I'm not taking in enough. Then and only then will I go and break down my fats. Then and only then will I do lipolysis. So again, the lip is fats, lysis is breaking down. So actually lipolysis. So only after I've depleted my glycogen will I go and break down my fats. So I always have an order of operation with this. And my fats, of course, are my long-term storage. So now let's get into the nitty-gritty of how I make my fats. So the first thing I'm going to do is I'm going to do lipogenesis. I'm going to make fats. So I'm going to put stuff in my long-term storage, stuff being energy, because I'm taking in way more fuel than I need. So with every process that has kind of a forwards and a backwards, a making and a using, we said pay attention to the trends because they'll be analogous. The making and the breaking process will be analogous. So making and breaking fats is no different. Making is analogous to breaking, or breaking is analogous to making, whichever way you want to look at it. So we have some steps that we need to do. One is we need to get on the correct side of the mitochondrial membrane. So you can reason your way through this one. So here's what we need to do. We said that acetyl-CoA equals energy. The reason we said that is I want you thinking if I have acetyl-CoA, I have energy. If I don't have acetyl-CoA, I don't have energy. But if I don't have acetyl-CoA and I need energy, I better get it from somewhere. So in this case, what I've done is I've made acetyl-CoA with the end goal of making energy in mind, except I just don't need it. So I made acetyl-CoA with the end goal of making energy in mind, so I must be in the mitochondria, and I am. But we had our most of the time rule. Most of the time, I do energy-making stuff in the mitochondria, glycolysis, of course, being the exception to that, making the most of the time rule as opposed to the all of the time rule. And I do storage stuff in the cytoplasm. Well, fat, by definition, is a storage process. I need to get to the cytoplasm. So I'm going from the mitochondria to the cytoplasm. Then I need to make my fatty acids. I need to make my glycerol backbone. And be okay with that word backbone. That means that the glycerol is the molecule that holds the three fatty acids together that become the triacyl glycerol or the triglyceride. Then I need to put the fatty acids and the glycerol together. So no one reaction or anything in this is difficult. The hard part is keeping track of where you are. So which step are you on? So we'll do the first step first. So first step is the correct side of the membrane. So I have acetyl-CoA. I kind of roadblocked in a way at acetyl-CoA because I made the acetyl-CoA with the end goal of making energy in mind, but the Krebs cycle shut down because I had enough energy. So I'm sitting there with this acetyl-CoA in the mitochondria with kind of nothing to do with it because I don't need the energy. So I'm going to save it for later by incorporating it into a fatty acid, using it as a building block of my fatty acid. But here's my problem. I need to get into the cytoplasm, and acetyl-CoA can't cross the mitochondrial membrane. So I'm going to convert it into citrate in the usual way. Put the oxaloacetate in. Citrate synthase is my enzyme. Actually fire up the first reaction of the Krebs cycle. So I'm going to make my citrate, but I'm still in the mitochondria with it. So then my citrate can cross out. So my citrate will cross the mitochondrial membrane and go out to the cytoplasm. That's why I made it. But I'm not using citrate to build my fatty acid. I'm using acetyl-CoA, so I need to convert it back to acetyl-CoA. I'll take the oxaloacetate back off, but I use a different enzyme. Remember, citrate synthase catalyzed an irreversible reaction, so this isn't reversing an irreversible reaction. I'm changing the enzyme and making it a new reaction that happens to go the opposite direction. So the enzyme going the opposite direction isn't particularly important, but since this is irreversible, I just pointed out, so you realize, yeah, I can go the other way. I just need to do it with a different enzyme. So I have my acetyl-CoA back. I have acetyl-CoA in the cytoplasm. So I'm good to go now making my fatty acid. So now I'm going to make myself a fatty acid. So first thing I'm going to do is the regulatory step. I have an acetyl-CoA. I'm going to convert that to malonyl-CoA. This is a carboxylation, so I have carbon dioxide going in, giving me that third carbon. I have a 2-carbon molecule that's becoming a 3-carbon molecule. The enzyme I need to do this is acetyl-CoA carboxylase, and it just so happens to be the regulatory step. I also need something else to do this. I need a molecule of a B vitamin. I need biotin. Really common thing to get asked. So I need biotin for my carboxylation reaction. Let me remind you again, on your vitamin chart that you drew, make sure you put whatever notes on there so you can pick up on this question however specifically or generally it's asked. Which of the following B vitamins do I need for a carboxylation reaction? Very general. Biotin. What B vitamin do I need for the regulatory step of fatty acid synthesis? Biotin. What B vitamin do I need for the action of acetyl-CoA carboxylase? Biotin. So again, going from very general to more specific, it's really just the same question worded different ways. So I have this malonyl-CoA now. So now I'm going to go find myself a molecule of fatty acid synthase. I'm going to put those 2 carbons on from the malonyl-CoA. I had the 3, get rid of 1, have 2. I'm going to repeat that way. This is the enzyme that we were calling the hand-holding enzyme. And when we told the story in class, I was fatty acid synthase, and all of you guys were 2-handed 2-carbon acetyl-CoAs. So we said my job as fatty acid synthase was to get 8 of you 2-handed 2-carbon acetyl-CoAs holding hands in a chain to make that 16-hand or 16-carbon chain that is palmitate. So what I did was, you guys were all wandering around the room. I grabbed somebody in my left hand with my left hand, and I grabbed somebody with my right hand. But my hands are tied up, and I want to get 8 of you holding hands. So what I need to do is I need to send the person who's holding my right hand over to hold my left hand. Before we can do that, though, or before you go, the 2 carbons that is there, that bond, we've got to reduce, dehydrate, reduce, then we can add. So then we'll send those 2 carbons over. Now my right hand's free. I'll grab one more of you two-handed two-carbon acetyl-CoAs with my right hand. Now I want to send you over. I've got to reduce, dehydrate, reduce. Then I can add you another two-handed two-carbon acetyl-CoA. Then another two-handed two-carbon acetyl-CoA wandering around. I'm going to reduce, dehydrate, reduce, and add. I'm going to keep going like that until I get a 16-carbon unsaturated chain, and we call that 16-carbon unsaturated chain palmitate. But, you ask, when I'm reducing, dehydrating, reducing, remember redox reactions, redox. I can't reduce without oxidizing. I can't oxidize without reducing. So when I was reducing, what was I oxidizing? I was oxidizing NADPH. Don't forget it's NADPH. Of course, if anyone asks you that, your distractors would be NADP, NAD, NADH, all kinds of NAD stuff. So NADPH is what I'm oxidizing. So I get that 16 carbon chain that's unsaturated. I might want something longer and or saturated. If I want to do either one of those two mixed functions, in reality it'd be an and, not an or, but we say if I want to do either one of those, I use a mixed function oxidase to do that. And then I'll make my 18, 20, whatever carbon chain. Oh, I'm sorry, that should have been saturated. Yeah, saturated. Oops. Really wrecking the diagram. Yeah, saturated molecule palmitate. So if I want to desaturate it, have an unsaturated chain, that's one of my mixed functions. So if I want to add a double bond or add carbons, and in fact, I'm likely doing both, mixed function oxidases do it. Okay, so I have a fatty acid, I do it again, get another one, do it again. So then I have 3 fatty acids, I'm ready to make my glycerol backbone. And in fact, I want to make glycerol 3-phosphate. So that's my backbone. So be comfortable with that term backbone. That's what holds my 3 fatty acids to make a triglyceride. So what I want is I want a molecule of glycerol 3-phosphate. So I have a couple ways of getting it. One is I could take a dihydroxyacetone phosphate that I got in glycolysis. I can use glycerol 3-phosphate dehydrogenase. I can do an oxidation reduction reaction, and I get glycerol 3-phosphate. Or I can take a plain old glycerol and I can phosphorylate it using glycerol kinase and get my glycerol 3-phosphate. Here's one of those places you want to really pay attention to the fact that these are reversible reactions. When I go to break down my glycerol backbone, when I'm breaking down triglycerides, I'm going to use these reactions. One of them I'm going to turn around. One of them I'm going to do nothing with. I'm going to leave it just the way it is. So pay attention to that. This is the one I'll actually turn around. You might want to note that so it's very clear to you. You don't need to learn the reactions again. You already have the reactions down. So now I have 3 fatty acids and I have my glycerol backbone. So now I'm going to do my last step. I'm going to put the whole thing together. So I'm going to put my triglyceride together. So I have my 3-carbon glycerol, and I'm just going to draw the carbons, and I have my fatty acids. So I want to join these. I want to form my ester bonds. That's how I connect them. So I'm going to join the first one, using an acyl transferase. So step 1 is an acyl transferase. Join the second one with an acyl transferase. Before I can join the third one, though, I have that other step that's a really easy step to forget. I need to get this phosphate out of here. So I need to get it out of there. I'm going to use a phosphatase to remove the phosphate. Don't forget that step. If you don't remove the phosphate, you're making an entirely different molecule. You're making a phospholipid, which, as you know, is the membrane component, things like that. So a whole different molecule. So I've got to get the phosphate out of there. Then I can join the third fatty acid with an acyl transferase. So now I have a triacylglycerol or a triglyceride, synonymous names, and I can send that off, put it in the bloodstream, ship it off to wherever I'm going um, with that. So that's the quick run through making your fatty acids and making your triglycerides. So now let's do the quick run through of breaking them down. So same steps, kind of. So I'm going to do lipolysis, lipolysis. But the lipo is fat, the lysis is breaking. So this is when I'm running at a sustained caloric deficit. Of course, if you eat somebody else's fats and triglycerides, you're eating a nice big marbled ribeye at the Outback or whatever, it's the same reaction steps, whatever, that you use to break them down. We always talk about it like we're breaking down our own because that's really more the application scenario than I ate a steak. So I've got the same steps, kind of. I have the triglyceride put together, so I've got to separate the fatty acids from the glycerol. So I can break them down. I need them separated. Then I've got to break down my glycerol, made my glycerol, break down my glycerol. Awfully similar processes. Then I've got my membrane thing, so a little bit different order. I've got to get on the correct side of the membrane. Well, which side is that? Well, reason your way through it, just like we did before. Fats are a storage molecule, so where are my fats? Where do I do storage stuff? I do storage stuff in the cytoplasm. Well, if I'm breaking down fats, what do I need? Well, I need energy. If I didn't need energy, I wouldn't be breaking down my fats. So I need acetyl-CoA, I need energy. I do energy making stuff in the mitochondria. So I need to get into the mitochondria. Then finally, when I get into the mitochondria, I'm going to break down the fatty acids, which this is my beta oxidation. So first thing we've got to do is separate the fatty acids. Pretty easy. So I have my glycerol backbone, and I have 3 fatty acids attached. That's my triglyceride. I'm going to use an enzyme called a lipase. So, a lipase, also known as a hormone-sensitive lipase, because we have that secondary messenger amplify the signal story going on, abbreviated sometimes HSL. That's going to separate my fatty acids from the glycerol. Now I've got both halves to deal with. I've got the glycerol to deal with, I have the fatty acids to deal with. So we'll deal with the glycerol first. That's nice and easy because you already know it from the making. So I'm going to break down my glycerol. So what I have is a molecule of glycerol, plain old glycerol. So first thing I'm going to do is I'm going to convert that to glycerol 3-phosphate. And again, let me remind you, I know you're tired of hearing it, but that's okay, 'cause by when you get tired of hearing it, you'll remember. Let me remind you, any word that starts with G, write it out. Don't abbreviate it. You're safe abbreviating F for fructose, P for phosphate, things like that. But there's so many G words. So write them out. So the enzyme I'm going to use to put the phosphate on, of course, is glycerol kinase. This should look really, really familiar from making the glycerol 3-phosphate when we were making the backbone for the triglyceride. Then I'm going to take the glycerol 3-phosphate and go to DHAP with it. So this is my redox reaction, just going the other way. Same enzyme, same everything. So it's the reaction you did and know, you just turned it around the other way. Now I've got that DHAP. Now what am I going to do with it? Well, you can go to glycolysis, gluconeogenesis, whatever, depending on, you need energy. Oops. But remember, gluconeogenesis always trumps everything. Do I need glucose? So if I need glucose, I'll go to gluconeogenesis. If I need energy, of course, glycolysis. So that's my glycerol taken care of. Now I've got the fatty acid, I've got to break it down. So now what I'm going to do is I'm going to take the fatty acid, but my problem is I've got a fatty acid in the cytoplasm right now. So I've got to get that fatty acid into the mitochondria. So I'm going to do that with the carnitine shuttle. So I have a fatty acid, and I've done what's called activate it. I put the coenzyme A on there, but that's actually the part that gets me stuck. So I've got this activated fatty acid out in the cytoplasm. So it's got to cross both membranes. It's got to get across the outer mitochondrial membrane. It's got to get across the inner mitochondrial membrane because I want to get it into the matrix. So it crosses the outer mitochondrial membrane with no problem. Don't let anyone trip you up into saying it has any trouble getting across the outer membrane. It doesn't. But the way somebody would try to trip you up on that is this. We have an enzyme that lives in the outer mitochondrial membrane because it works in the intermembrane space. The enzyme's name is carnitine acyl transferase 1, also known as carnitine palmitoyl transferase 1. What that enzyme does is this. Takes the CoA off and puts the fatty acid, attaches it to a molecule of carnitine. So it takes the CoA off, puts the carnitine on, or takes the fatty acid off of the CoA and puts it onto a carnitine, whichever way you want to look at it. So either way, I end up with a fatty acid attached to a carnitine, and I dropped off the coenzyme A. Because remember how shuttles work. Shuttles either convert what won't cross the membrane into something that will, and cross, and then convert it back to what you wanted in the first place but wouldn't cross, or they drop off the part that gets you stuck and cross, then get you a new one of those parts that got you stuck when you get there. So either way, when you look at just the reactions without the Y, you're going to see some kind of doing and undoing, making and unmaking. I took this off and put it on. I turned it into something else and turned it back. When you see a reaction like that and you're looking at it thinking, why am I doing that? I'm doing and undoing. There's going to be a crossing the membrane, either in or out, story in the middle of that as your Y. Okay, so I've got a fatty acyl coenzyme A now, or fatty acyl carnitine. That's going to cross. So I've got a fatty acid attached to a carnitine now in the matrix. That's where I want this thing. So I'm in the place I need to be in, but I don't have fatty acid attached to what I want it attached to. So I have another enzyme called carnitine palmitoyl transferase 1 or 2, or carnitine acyl transferase 2. It lives in the inner membrane because it works in the matrix. So what it does is it takes the fatty acid that's attached to the carnitine, finds you a new coenzyme A, takes the fatty acid off of the carnitine or the carnitine off of the fatty acid, and puts the CoA on. So now I have what I needed. I have what I wanted. I have a fatty acid attached to a coenzyme A, and I'm in the mitochondrial matrix with it. So that's my carnitine shuttle. That's my ticket into the mitochondria. I drove my car into the mitochondria. So now I'm good. I've got a fatty acid in the mitochondrial matrix. Now all I've got to do is break it down. So now I'm going to break down my fatty acid. This is my beta oxidation. So this is probably the biggest diagram in any biochemistry book because it's the same reaction done over and over. So think your way through how we did this. We built the fatty acid 2 carbons at a time. We said a couple of things, or we say a couple of things when we're talking about fatty acids. We say fatty acids are kind of sort of a whole bunch of acetyl-CoAs hooked together. And that's mostly true. What I should be saying is that it's the carbons from those acetyl-CoAs all hooked together. But what I want you to be thinking is acetyl-CoA equals energy. So if you're thinking fatty acids are a whole bunch of these molecules that equal energy all attached together, that makes you think that a fat's lots and lots and lots of energy, which is a correct thought, and that's why I want you to have it. The other thing I want you thinking is we build and break these 2 carbons at a time. Well, that should make sense because we build them and break them out of acetyl-CoA. So we either have an extra acetyl-CoA or need acetyl-CoA. Well, that's a good thought too because acetyl-CoA equals energy. We either have too much energy or don't have enough energy. And that thinking in 2 carbon units keeps you on track of what you're storing or getting. That is the acetyl-CoA. So beta oxidation was the story where we drew the picture and we just did the same reactions over and over. So for the sake of space here, I'm going to do, I don't know, an 8 or 10 carbon fatty acid. And I'm only going to draw the carbons, and I'll put a CoA on the end because it's activated. So what I want to do is this. I want to take off these 2 carbons with the CoA attached because that'll be my acetyl-CoA. So that's my goal. So before I can do that, I've got to do some stuff to this bond. Here's what I have to do to this bond. I need to oxidize it. I've got to hydrate it. And I've got to oxidize it again. Then I can cleave it. This sounds kind of familiar. So we said that making and breaking processes are analogous. Remember what we were doing when we were building the fatty acid. Remember that reduce, dehydrate, reduce, and add thing? We reduced, we dehydrated, we reduced, and then we added the carbons from another acetyl-CoA and did it again and again and again and grew the chain that way. Now we're going to oxidize, hydrate, oxidize, and cleave. So I'm going to oxidize this bond while I reduce FAD to FADH2. Then I'm going to hydrate it. I don't get anything out of that. Then I'm going to oxidize it while I reduce NAD to NADH. Then I'm going to cleave it. I'm going to take 2 carbons off with a CoA attached. Kind of sounds like an acetyl-CoA because it is. And I stick a CoA over on the end of that chain. So now I have 8 carbons. 2, 3, 4, 5, 6, 7, 8 with a CoA. I want to do the same thing again. I want to take the 2 carbons with the CoA off. So same thing again. I'm going to oxidize while I reduce FAD to FADH2. Hydrate, don't get anything. Oxidize while I reduce NAD to NADH. Cleave it. Gives me an acetyl-CoA. Put a CoA on over here. And I'm going to continue, and I'm going to keep doing that. I'm going to keep doing that until I get down to 4 carbons. So when I'm down to 4 carbons, don't forget, with my CoA on the end, I'm focusing on these 2 with the CoA. I'm going to oxidize while I reduce FAD to FADH2, hydrate, oxidize while I reduce NAD to NADH, cleave it, get an acetyl-CoA, put a CoA on over here, so that's an acetyl-CoA also. So my last cleavage, don't forget, when I have an even number of carbons, produces 2 acetyl-CoAs. So then your questions are always going to be the how many questions. How many NADH? How many FADH2? How many cleavages? How many acetyl-CoA? So those will always be the beta oxidation questions you're going to get. So you're tired of hearing me say it, but that's okay. Draw it. Let's say you asked about a 16 carbon fatty acid. Draw out 16 carbons. And then just do it. It's way too easy to make mistakes on this. So I'm going to cleave here. Before I can do it, I get a FADH2, an NADH. I'm going to get an acetyl-CoA. Here, again, again, again. And don't forget, this is just an acetyl-CoA here. This last one is my leftover. I don't have to work for it. So how many of everything did I get? Well, how many FADH2s? 1, 2, 3, 4, 5, 6, 7. 7 FADH2s. How many NADHs? 1, 2, 3, 4, 5, 6, 7. 7 NADHs. How many cleavages? 1, 2, 3, 4, 5, 6, 7. 7 cleavages. How many acetyl-CoA? 1, 2, 3, 4, 5, 6, 7, 8. 8 acetyl-CoA. So take the second of your life to draw it, because the distractors will be numbers that you would get if you make a mistake. So whoever's writing your question is staying one step ahead of you with the distractors, anticipating your mistakes, giving you the answer that you would get if you made that mistake. So one last thing we need to do, and then that'll be it. Let's say I have an odd number of carbons. I'm just going to do 9 carbons just for space. Obviously, the fatty acid would probably be longer. But let's say I have 9. So 1, 2, 3, 4. We're going to do exactly the same thing to a point. Before I cleave that, FADH2, NADH, acetyl-CoA, again, and again. And that's it. Once I'm down to 3 carbons, I'm done. I can't do anything else. Those 3 carbons are propionyl-CoA. So the last cleavage, when I have an odd number of carbons in my fatty acid, I was eating at Ronald McDonald's or whatever, that last cleavage is going to give me an acetyl-CoA and a propionyl-CoA. Remember your numbering, you're counting, meth-eth-prop. Prop is 3, I have 3 carbons. So the last cleavage gave me the propionyl-CoA. Then the propionyl-CoA will give me a succinyl-CoA. So the cleavage does not give me the succinyl-CoA. The propionyl-CoA gives me the succinyl-CoA. So again, do all your counting, draw it and count it. I got 3 FADH2s, 3 NADHs, 3 acetyl-CoAs, and of course 4 would be a distractor. Then got that propionyl-CoA. So again, draw it. Of course, the succinyl-CoA is literally energetically halfway through the Krebs cycle. It'll go and give me 6 ATP. I think that's everything for reviewing the fatty acids. And of course, let me remind you again, the Brightspace videos are a longer, more detailed version of it. This is just the quick review version of it.